We all know that deep learning has made a huge amount of progress in the recent past, right? And we also know that AI, which is artificial intelligence, is certainly scaling across applications. They include image analytics, security, transportation, customer, you name it. In fact, interestingly enough, AI, the IBM's AI lost to Harish Natarajan in a debate last year, but still at that time, the IBM AI was actually quite persuasive. And if I really look at AI scaling across applications, it's also scaling across investments and people. So today, if I really look at the number of papers which are being submitted to some of these machine learning conferences, they're mind-boggling. The numbers are probably in the range of 9,000 to 10,000 in some cases. AI is also scaling across investment. It's skyrocketing. And if I also look at the number of courses which are being offered and the enrollment in some of those courses, even at Purdue, they're really through the roof. A few other instances where AI sort of has been beating natural intelligence sort of got started back in 1997 when IBM Deep Blue beat Kasparov, and that was a big big deal. Following that, in 2011, IBM Watson again beating Brad Ritter and Ken Jennings, and finally in 2016, Google AlphaGo beating Lee Sedol 4-1. Now, certainly AI is, these days is going to be extremely difficult for the humans to beat AI in any one of these games. But the question, of course, is at what cost? Turns out that if you look at all these, super heavy computers, they are really, the power consumption requirements are of the order of, hundreds and thousands of watts. So, and then compared to that, if you look at brain, that's probably about 20 watts or so. There's a huge energy efficiency gap that exists today. Now on the other side of it, if I go into a little more details and try to look at the AI compute demands, and that's also kind of mind-boggling. So what I'm showing here is the number of operations, and in this particular case I'm showing it in terms of zeta operations on the y-axis versus different kinds of ML or machine learning application that I'm showing, game, language processing, image classification, optimization, and so on. It turns out if I take an example of the network architecture synthesis, which is let's say implemented in a large transformer network, turns out that the corresponding power consumption or the carbon emission would be almost 315x higher than the air travel from New York to San Francisco per passenger. Or if you consider, for example, the lifetime of a car, that's about 5x higher than the lifetime of a car. That's mind-boggling. And that's on the other side of it, if I were to really look at edge applications. And to that effect, actually, we did an analysis of a simple case study of object recognition using a smart glass with a state-of-the-art accelerator. In this particular case, the accelerator was a Google Edge TPU, and I'm showing an example of a flight attendant sort of wearing that glass and recognizing their important customers. Turns out that analysis really shows that if I do an analysis of implementing object detection, which is a retina net on the smart glass, without going into details of it, it turns out that time to die for the battery is going to be actually about an hour. Now that's under ideal conditions. Now, if you consider the fact that there are a lot of non-idealities in the system, the battery life is probably going to be about half an hour or so. And again, that's also not sustainable. But then again, the question, of course, is where do these inefficiencies come from? Now, they come from algorithms, hardware architecture, and the circuits and devices. And I'm going to be covering some of those as we, in this talk. Now, beyond the compute demand, certainly one has to think about in the world of AI, can I learn with less data? Today, machine learning applications require a humongous amount of data. So, in order to make it more efficient, the question is that can I learn with less data? On the other side of it, turns out these systems are sort of black boxes. Sometimes we don't know why they work, and sometimes we don't know why they don't work. And I'm giving you an example of a problem of sort of generalization, where I'm showing actually a chair, and my network learns that that is a chair, Now the question that really comes is that if I now show as a test case that the bottom chairs, would my system really recognize them to be chairs or not? No, it really depends on certainly the the features and the context they're in. So of course our system, we would like them to be generalizable and to be able to actually recognize those to be chairs too. Interestingly enough, as I said, it's a black box, and there's some very, very interesting thing that happens in a system, AI system of today. There's a huge robustness problem. Now, if I'm in this case, I'm showing actually an example of a macaque, which is on the left. And if I train my system basically says, as a test case in this case, says that it's a macaque with a very high confidence. Now, what I do is, now if I end up adding some crafted noise to this macaque, which is shown there, it's an adversarial perturbation that I add. Turns out the equivalent image that I get, which is on the right, to a human eye, there isn't really any difference between the left image and the right image. However, now my system, with that little noise that I added, makes it with a very high confidence, it's a bookcase. So that's a real problem. So can I really, can we really solve such problems, make our systems robust? And finally, most of these networks of today actually suffer from what's called catastrophic forgetting. If your system learns task 1 followed by task 2 followed by task 3, it turns out it actually does a good job of learning task 3, but might have forgotten task 1 and task 2. Whereas we humans, actually, we don't do that. So is it possible then, of course, can we incrementally learn sort of in a lifelong fashion? So these are actually sort of open problems. There's a whole bunch of work that is going on, but still we don't really have a really good solution to these problems. Now, so far I've talked about these challenges, and turns out, and hopefully it's clear by now, that in order to solve these challenges, or at least tackle some of these problems, you have to look at the problem all the way from algorithms to architecture. To that effect, I mean, you have to really develop the right kind of neural algorithms, followed by the hardware architecture and the devices that these neural algorithms are going to be implemented in. So the obvious question then is that what should these algorithms be? How should these architectures be in order to really have an efficient system? So to that effect, the question is, can we really take cues from the brain? As an example, and I'm going to more details of that in just a minute, but the question, of course, is, hey, can I take the right kind of neuron model that we have in our brain? Can we use the right kind of learning algorithm, the computing principles of the network topology? So if I had to go into a little more details of it, what kind of neural models are bio-plausible? Can I really use the Hodgkin-Huxley kind of model? Or should I use a little bit simplified, spiking neural model like the weakly integrated fire or integrate and fire? I'll go into that in just a minute. But also there are actually stochasticity which is observed in the brain. So to that effect, can my neurons be stochastic neurons? What kind of learning algorithms should I use? Turns out, backpropagation that has been used as an optimization procedure for learning has been in the standard artificial neural networks domain. It has been used quite a bit. And that's a global kind of learning. But on the other side of it, researchers have noted localized learning called spike targeting, which has been observed in the hippocampus. Question is, can I use such localized learning that can potentially be faster? Can I use that and still? On the other side of it, what kind of network topology should I have? Long-range connections? Should I have feedback connections? Should the network be similar to what we observe them to be in the visual cortex? Should I be computing with spikes, or should I compute with analog values of the inputs? Should I have a tightly integrated compute and memory? I'll go into that later on. Should I have asynchronous event-driven computation with spikes? And finally, at the end of it, you certainly have to represent the inputs that are going to be coming to your system. How should they be coded? Should they be coded in as a rate coding technique? Should there be time-based coding? Should I have other kinds of coding that can potentially be useful to actually have a network to learn better? So with that in mind, I'm going to first talk about the learning algorithms, and these are bio-plausible learning algorithms that we look at. And the reason I'm going to focus on bio-plausible learning is that at least we have an existential proof that our brain does well. So if you can take cues from the brain and try to come up with learning algorithms, the kind of neurons and synapses that we use, potentially we can lead to an efficient learning. So with that in mind, let me go into a little more details of the neuron models. So if I had to really look at a biological neuron or a spiking neuron, I'm showing a biological neuron with the synapses shown there. And so if I have a bunch of input spikes that come in, it turns out that the membrane potential of the neuron changes. And so if there are spikes comes in, the membrane potential goes up. And if there are no spikes, then the membrane potential beyond a certain point starts decaying. And if there are more spikes that comes in, it actually starts growing again. And finally, at the end of it, when it reaches a threshold, it actually switches. Now, this kind of behavior, which is a leaky integrate and fire kind of behavior, can be represented by a standard, a simple RC circuit. And that's the equation for that circuit is shown there. Now, on the other side of it, if I have to really think about other kinds of neuron or simplified neuron, what one can do is rather than having an leaky integrate and fire kind of neuron, it's possible certainly I have an integrate and fire neuron, but I get rid of the leak part of it. So when I implement it in a hardware, it becomes easier to implement in some ways. Maybe I lose out on something, but maybe it's still good enough and can potentially give me efficiency in terms of learning and energy. Finally, as I mentioned earlier, that neurons in the brain at least have shown some stochastic switching behavior. So with that in mind, is it possible that my neuron transfer function should be stochastic in nature and can look somewhat like this stochastic sigmoid function that I'm showing there? So these are all possibilities of using sort of bio-plausible neuron models. Now, on the other side of it, so far I talked about the neuron model. The question, of course, is, hey, can I do synapses? How do the synapses behave? They will be storing the information that they'll be learning. So to that effect, how should my synaptic updates be? As I mentioned earlier, in the earlier slide, there's something called localized learning, and which has been observed in the hippocampus of rats, and this is also called spike timing dependent plasticity. So for that learning, I'm showing a very simple example of an output neuron O1 with some input neurons I1, I2, and I3 with synaptic weights of W1, W2, W3. Now, if you take an example of some spikes that might come in, as an example, let's say the output neuron O1 spikes at a particular time, which is shown in red, and you have some input spikes that were coming in, which were at a particular time for neuron I1, another one for I3. Now it turns out, and if you look at this simple figure, it shows you that O1 was switching, the output neuron was switching most probably because of the switching that happened on I3. And that if you look at the timing difference between the output and the input, then I should really say that, hey, that neuron caused that switching, so I'm going to have some synaptic updates because of that. So what I'll do is I'll have a synaptic update due to that, which I'm going to call potentiation, and that potentiation is going to be larger than what I'll potentiate W1 by. Now, so that basically depends on the correlation that I have between the input timing and the output timing of these spikes. But on the other side of it, if you really think about it, if these neurons are not correlated at all, then of course, I should depress the weights. So in this particular case, if the neurons are not correlated at all, what I'm showing on the right, that I2 was spiking later than O1 spiking. Of course, these two are not correlated, so I'm going to depress the weights. So with that in mind, these kind of updates, synaptic updates, which are all localized updates, one can certainly do some learning. Now, we can also observe that this kind of learning is probably going to be unsupervised, or potentially, as we'll see later on, can be made into a semi-supervised learning. Now, on the other side of it, the deep learning community certainly has been using back propagation based learning. So what is a back propagation based learning? It's a global learning. And I'm showing an example of a neural network here where I'm showing, let's say, an image of a cat. And I initialized all my weights to start with to be random, let's say. And then I have if I show the picture of a cat, what's going to happen is that there's going to be some spikes going through these networks, and at the output I get an indication whether it's going to be whether it's a cat or a dog. So let's say if it's a dog and rather than a cat, then of course what I have to do is I say there's a loss at the output. How much is that loss? Because I'm recognizing a cat as a dog, that loss is what I'm actually mathematically going to be representing, and then I'm going to be backward propagating through this network all the way to the input so that I keep on updating the weights. So after a few iterations of these, showing the different data set that I might have, at the end of it I end up learning a cat to be a cat and a dog to be a dog and a cow to be a cow. So this is a globalized learning, and that's sort of been used quite a bit using stochastic gradient descent. Things become a little bit different when you start to use it as a spiking neural networks. I'm not going to go into the mathematics of it, but certainly you have to use not the standard gradients but some sort of a surrogate gradient back propagation to actually get your updates properly. So with that in mind, the question then becomes, can I really train, large-scale neural networks? So far, in the last, there's been a good amount of progress that's been made in the last few years, but it was difficult to really train large-scale networks, spiking neural networks. So one of the things that we did in our group is to actually come up with techniques to, train large-scale, spiking neural networks. So if I were to really think about, in this particular case, I'm going to show a very simple example of training with both stochastic, or spike time independent plasticity based localized learning and some back propagation based learning. So in this particular case, actually, I'm going to not use the standard, spike time independent plasticity based learning, but I'm going to call it a, stochastic STDP, and that actually we'll see later on has some really benefits on coming up with a good amount of model compression. So with that in mind, let's say that I start with a network. It's a convolutional network with few layers. I'm going to show some inputs, and the learning, as I said, in this particular case, based on spikes, input and output spiking activity, I'm going to use that spike time independent plasticity curve that I showed earlier for both depression and synaptic updates that I'm showing over there. And with that in mind, I actually can now come up with a network that can potentially learn. Now, the spike timing dependent plasticity that I'm using in this particular case is, remember I talked about the fact that when the output neuron spikes, it's certainly related to some of the activities of the input neurons, right? So T pre, the time when the pre-neuron spikes minus the time when the post-neuron spikes is an indication as to how much I should update my weights by, and that's given by delta W. So rather than doing that, I can potentially say, hey, is it possible that rather than updating the weights by delta W, can I update the weights by some probability which is actually related to delta W? In other words, I'm going to assign a probability which is associated with P delta W and say, hey, the weight can potentially be a value of R on or R off based on this probability. So with that in mind, now I can train this network. So these networks are all going to be binary networks, binary in terms of activation, binary in terms of the weights. And finally, I need to have, since this network actually was doing unsupervised learning, at the end of it, I actually connect a couple of fully connected layers, which is trained using back propagation and with the labels that I have now, and that could be animals, birds, cars, and so on, and I can do these, hybrid kind of learning. Turns out that, and we'll talk about that again later on, there's a problem of what's called the vanishing spikes. So when you have the networks, in the later layers of the networks don't have enough spikes. So in order to take care of that now, you probably have to come up with a better network design, and in this particular case, actually use some direct connections or the skip connections, and it turns out if you do that, now you're able to train these larger scale networks. So what kind of results you can get? The key findings are that using such an approach of stochastic STDP localized learning and a little bit of global learning at the in the last couple of layers, it turns out it can give you a huge amount of memory compression. In case of simple data sets like MNIST, which is digit recognition, it turns out you can get almost 40x memory compression under ISO accuracy conditions. And if you look at a little more complicated data sets like CFAR 10 and so on, you almost get about 20x improvement in memory compression. What else? It turns out that certainly these can be implemented directly, and we did that. Using CMOS transistors. Now, implementing some of these stochastic functions that I was talking about, stochastic STDP or the stochastic neurons, are complex. The number of transistors or the CMOS transistors required might be order of about 15 or 20, but certainly it's possible to implement that, and it's possible to get a good amount of improvement. And in this particular case, it was possible to get about 23 tops per watt, which is a measure of how effective or how efficiently you can do that with the amount of power, the least amount of power consumption. Now later on we'll see that CMOS may not be the best choice. CMOS is certainly good as an on-off switch. However, for synaptic or for example neuronal implementations of these circuits, it turns out you can potentially do better with some of the emerging devices, and I'll talk about that a little later. Now, with that in mind, one can also go a little bit more complex and say, hey, is it possible that rather than really looking at the kind of simple data sets and all that I was talking about, is it possible that I can fly drones, and I can fly drones very effectively in an energy efficient way? Today, when you want to fly a drone using only cameras and nothing else, that's actually can be quite problematic. So is it possible that I actually design a system where I'm going to do optical flow, have the right kind of sensing capability, do optical flow, depth estimation, and object recognition? And if I do that, would I be able to now fly my drone effectively, faster, and with energy efficiency, with a longer flying time? So to that effect, the sensors that we looked at in this particular case are the event cameras. And these event cameras are kind of interesting. They provide spikes. When there is a relative motion between the camera and the objects, then it actually produces spikes. And if there is no relative motion, in that case, for each of those pixels, there would not be any spike. So in other words, these are actually very energy efficient cameras. And with those energy efficient cameras, the question then becomes, hey, is it possible that I can build a good system of optical flow and depth estimation, object recognition, and fly faster? So I'm actually showing an example of a optical flow estimation in this particular case. This is using actually a combination of the spiking neural networks that I was talking about, which are more bio-plausible, and then I have in the back end I have an ANN, or the standard deep learning network. And the reason why this was done is the inputs in this particular case comes in spikes, and as I said earlier, there's a spike vanishing problem. So to take care of that vanishing problem of spikes, the later part of the network is actually a non-spiking network. So it's a hybrid network, and this hybrid network can actually give you really good amount of energy efficiency. And if I'm able to play this video, I don't know if I can. It turns out that let me try to play this video. So in this particular case, if what I'm showing here is my student going in front of the camera, and you can basically see that the spike image on the left and the predicted optical flow on the right. So this is basically showing that it's possible to actually do it very efficiently. I'm not giving you the energy numbers, but it's quite quite a bit more efficient than the standard way of doing deep learning. So in this particular case, as you can see, bio-plausibility leads to not only energy efficiency, but in this particular case, actually higher fidelity in my predicted flow. You can do actually a few other things. In fact, in this particular case, actually, I have my student looking at the drone and asking, commanding the drone to go up or down based on these cameras. The network that I implemented in this particular case is a very simple-minded, a liquid state machine, which is basically a random connection of these, random connection of synaptic weights with forward and backward connection. Training is actually simple, but what I really wanted to show is that it's possible now to really implement such systems, in the spike domain. And the basic idea is that energy efficiency, and you can use it in drones. So going forward, so far I've talked about these algorithms that we've been looking at. So what kind of hardware should I use? Should I use the kind of hardware, the neuromimetic devices and hardware fabrics that can efficiently implement these algorithms in the proposed hardware? So to that effect, the hardware fabrics should be such that they not only efficiently implement the algorithms, but possibly embody the computing principles of the brain. So why is that important? Today, the most of the hardware is really a von Neumann machine. So what is a von Neumann machine? Basically, they have computing on one side and the memory on the other side of it. So, whatever little that we know of the brain, in our brain, we don't certainly have, computing on one side and the memory on the other side of it. In fact, interestingly enough, today's von Neumann machines are really bottlenecked by the traffic that you have between the memory and the computing unit. And that can be a huge bottleneck. So to that effect, can we really take the principles of actually something like what the brain possibly does, which is computing in the memory itself? So in other words, can I do near memory or in-memory computing? Turns out the things that we are talking about, AI, are error resilient. Most of it are error resilient. So can I really make approximations? So one can really, come up with good mathematical theory by properly approximating your systems so that you can still get the same, you can use less complex hardware while still being able to actually come up with, energy efficiency. Can I use a stochastic hardware? As I mentioned and I showed earlier, that stochasticity certainly helps in model compression, and in fact, it can potentially lead to better optimization. So stochasticity also is important, and we can potentially use it in our hardware to have efficiency. And finally, what kind of devices should I use? Should I use CMOS transistors, or should I really try to build new devices that are closer to what the neurons and the synapses are? And what kind of interconnects would make sense? So to that effect, there's been a good amount of work which has been going on. And this is actually on the right. I'm showing some of the research from IBM Research, showing the fact that for speech applications or language or vision, turns out for all these AI-related applications, the most important computation that you do are vector matrix multiplication or matrix multiplication. So the red basically shows how much of those matrix multiplication that you end up doing. So in other words, what we really would like to do then is to actually make these systems better. If I'm able to do this in-memory computing, and in particular actually these kind of vector matrix multiplication, if I can do it in the memory itself, then I can basically get alleviate the bottleneck that we have in the standard von Neumann machine. So where are we today? Today we certainly have multi-cores and GPUs, and we use that on a regular basis in our labs. There are different kinds of accelerators, but it turns out you can do much better by using, for example, different kinds of in-memory computing fabrics or stochastic fabrics. And finally, you can potentially, if you use those fabrics and the right kind of algorithms, the hope is that you can reduce the efficiency gap or the energy efficiency gap that exists today between the brain and these systems. All right, so let's try to look at some of these devices or the neuromimetic devices. So in this particular case, I'm showing a bunch of these very, very colorful devices. And for example, on the left, I'm showing a ferroelectric transistor. In the bottom, I'm showing actually a lateral spin valve. Some of these devices that I'm showing here can potentially act as both neuron and a synapse with some little modifications. What I'm going to be really focusing on is, of course, the question is CMOS going to be required then? CMOS is certainly going to be required in some of these computations, but CMOS may not be the most efficient one in directly implementing some of these neuronal and the synaptic functionalities that I'm talking about. As we'll see, some of these interesting devices with proper kind of device modification can potentially mimic the neurons and synapses with different kinds of biofidelity. So to that effect, what I'm going to be really looking at is in particular actually a magnetic tunnel junction as an example. With a heavy metal at the bottom, and such a device will see that can potentially mimic both the neurons and synapses in a very effective way. On the other side of it, I'm also showing a few other devices like a domain wall motion based device, which is also a magnetic device that can mimic the neurons and synapses, and other devices like the RRAMs or the PCMs or the phase change kind of memory devices can potentially also be quite interesting in terms of achieving the synaptic and the neuronal functionalities. So now if I were to really compare these devices, these non-volatile devices, non-volatile memory devices, and compare that to CMOS memories, where are they? Turns out this is kind of interesting. So if I look at the property of any memory, and then again synapses are all memories, turns out that if I look at PCM, RRAMs and so on, their endurance, which is shown at the bottom, is actually not much, 10 to the 7 or 10 to the 5 cycles. So what does it mean? That what it really means is that while these devices can be quite exciting and interesting as a synaptic device, turns out training might be more difficult to do in such devices because of the low endurance. On the other side of it, and if you look at a magnetic tunnel junction, the endurance certainly is closer to what a CMOS SRAM is, which is of the order of about 10 to the 15 or 10 to the 16 cycles. And so that can potentially be useful for both training and inference. A few other things which are also important to notice is the fact that the write energy of some of these devices turns out to be actually more than what the CMOS devices would have. Finally, another interesting thing to note is the fact that the cell area for example, a PCM or an RRAM is actually much lower than what you'd have in a CMOS kind of SRAM, or in fact even for a magnetic tunnel junction. So the advantages of a PCM and an RRAM are certainly being the footprint being very, very low, and that's something which is very important. I can pack in a lot of these synapses into a single chip, and since I have an endurance problem in such a chip, if I do put in a lot of these devices, I need to make sure that I don't have a DRAM. I don't want to bring my data back and forth between the DRAM and these devices and write and read constantly. So with that in mind, as I mentioned, I'm going to focus on these magnetic tunnel junctions as a possible option for using it for neuronal applications. Again, let's go back and try to look at the biological spiking neuron that I mentioned earlier, which is represented now by this Leakey integrate and fire equation, which is given by this simple RC circuit equation, which is shown there. The basic function of these neurons is that they basically would end up doing this dot product, which is shown by WJ times this current that I'm showing there. And then at the end of it, the neuron can potentially switch if it reaches the membrane potential. Now let's look at a very simple example of a magnetic tunnel junction. I'm not going to go into the details of a magnetic tunnel junction, but this is basically actually, you can potentially think of having two nanomagnets separated by a spacer. In this particular case, it can be MgO. And that's shown on the left. On the right, I'm showing a very similar device, which is again a magnetic tunnel junction, but it's placed on top of a heavy metal, and that can be tantalum. And what can happen in the right device, which I'm showing there in the heavy metal, if you have a current or a bunch of spikes that are coming into that heavy metal by an effect called the spin Hall effect or spin orbit torque, turns out that the free layer of the magnet can be switched. So this now on the right side of it, I'm really showing a 3-terminal memory device which actually has a magnetic tunnel junction. So in the magnetic tunnel junction actually has two of the magnets pointing in the same direction. The resistance of that device is actually lower than if they're pointing in the opposite direction. Okay? So now this is basically a non-volatile device which can be written, for example, with this heavy metal layer, and the read and the write ports of these devices are decoupled. So with that in mind, what one can also show that if I have a bunch of these, bunch of spikes coming in front of with input current, the magnetization or MZ of that free layer follows somewhat like, if you can see, that it follows like a leaky integrated fire neuron, or in other words, that can be really represented by the Lambda-Lifshitz-Gilbert equation, which is shown there, which is very, very similar to that leaky integrated fire operation that I shown there. And now this device can potentially be implemented directly as a spiking neuronal device. Now, it's difficult to use it directly, and the reason why it's difficult to use it is because of the fact that there's a leakage associated with it, there's a time constant with that leakage associated with it, and if it's not programmable, I might have problem implementing that directly into a hardware. So to that effect, that same device now has some very, very interesting property. The behavior of that device that I showed, the magnetic tunnel junction, is also kind of interesting. It has a switching behavior. If you remember that I showed this stochastic neuron earlier, the switching behavior of this device is a stochastic sigmoidal function that I showed there. So in other words, if I have a current that comes in and it tries to switch the device, due to thermal agitations, what happens is that this device is going to follow switching characteristics, which is sort of probabilistic in nature, as shown there. So now if you want the device certainly to switch with very high confidence, then of course you have to pump in a lot of current. But if you have a lower current, of course in that case it turns out it actually behaves as a stochastic switching device, and that's something interesting. Then potentially I can get an R-on resistance or an R-off resistance following that sigmoidal characteristics that I shown earlier. We actually did some experiments in our group in Berk, and we implemented actually a Hall bar structure, or in other words, I'm basically talking about a magnetic tunnel junction with the heavy metal that I shown in the earlier case, and on the right actually I'm showing the fabricated results that really shows that the behavior of this device is stochastic in nature. And that can potentially be used as not only a neuron, but also as a synaptic device. So now, if I were to really think about doing neuronal and synaptic computations with these spin transfer torque devices, you have a bunch of inputs that are coming in, and you have these synapses. You do this weighted summation operation, or the matrix vector multiplication that I was talking about earlier, and then you have a neuron which is going to do this thresholding function. And now if you do that, you can potentially implement that in a crossbar array, where you have a bunch of these inputs which are coming in can be voltage, and the output due to Kirchhoff's law is going to be actually a current that you get. And with that in mind, now you can implement the synaptic functionalities, or in fact on the right side I'm showing basically the neurons. So now if I were to implement that in a neural network, a simplified neural network is going to look somewhat like this, where you have a crossbar and a bunch of these neurons which are shown there. And in each of those neurons and synapses are basically very, very similar structures. They're not really any different. And if I look at this, you might say, hey, there's a potential for getting a huge amount of energy improvement from these devices over CMOS, because they can directly implement the synapse and neuronal functionalities. But things are not that easy. Turns out that when you try to implement these crossbars, this is an analog computation that you're doing. And with those analog computations, when you try to communicate with other kind of crossbar arrays, what you probably have to do, and these are the kind of devices that you can implement, what you probably have to do is you have to communicate using analog to digital converters. And if you do that, if you're using these analog to digital converters, what one can also show is that the power consumption, the energy consumption now is going to be dominated by these analog to digital converters. So what do? What you really need is larger crossbars. And how do you get larger crossbars? So the way to get larger crossbars would be to really come up with a way of doing device algorithm co-design. So that you look at the device, the crossbars, the algorithms, and you can bring in algorithmic sparsity, and along with algorithmic sparsity and the device optimization, so that you can have a better R-on to R-off ratio by, let's say, changing the oxide thickness and all. What one can show is that you can now, with sparsity and probably device optimizations and the algorithms, you can actually come up with larger crossbars, and you can now reduce the analog to digital conversion costs. So to that effect, one can certainly come up with a hardware architecture, putting these kind of crossbars into tiles and develop a network on a cheap architecture which is amenable to data level parallelism, and it's certainly highly efficient for machine learning inference. And what we found is that if we now compare that with, for example, today's GPUs with a batch size of 1, turns out you can almost get 100 to 1000x improvement depending on the kind of benchmarks that you implement. So with that, I'm going to conclude my talk. What I talked about today is bio-plausible networks with spike-based information representation. I don't want to give this feeling that spike-based computation is do-all, end-all. Certainly, it has this good possibility of achieving energy efficiency and robustness, and that to me are the primary advantages at this time. It certainly has a huge amount of potential for edge computing, for training, inference, and especially working with the event-driven cameras that I showed. We also looked at the possibilities of using these neuromimetic devices and devices like, for example, optimized magnetic tunnel junctions or SOT-based or spin orbit torque-based devices to do that, and that can potentially harness the synapse and neuronal functionality with high efficiency. Now, one thing that we are not using is the temporal domain. Even though in the spike domain we can potentially use timing, if we can effectively use timing, we can potentially learn better. And that's something that one certainly needs to look at. So I believe at the end of it, algorithm hardware co-design, guided by biological principles, can potentially be a pathway for the next generation neural computing. So I'd like to certainly thank my past PhD students, my past postdocs and master students, and my current students who really made all these sort of things happen. And so with that, thank you very much, and I can take any questions.